Alright, so today we are going to finish out questions 5 and 6 on 2017. I'll go ahead and say um, these questions kind of are tough. Well, the last part of 5 and then all of 6, I think it could be tough. Okay, it's just going back to those series problems, and those can be definitely the most difficult parts of Calc BC. But let's just jump into 5. Five's not too bad from the start, I don't think. Okay. All right. So let me get comfortable. A says find the slope of the line. Find the slope of oh my god. Find the slope of the line tangent to the graph of f at x equals 3. Easy enough, right? We want to know the slope line tangent. All you have to do is find the derivative and plug in 3, right? So let's say f prime of say f prime of x is equal to you can do low D high, you can do quotient rule. I think I actually did power rule here. I said 3 times 2x squared minus 7x plus 5 to the negative first, and when I did the chain rule there, it becomes negative 3 2x squared minus 7x plus 5 to the negative second, and then times the derivative of the inside would be 4x minus 7, which ultimately becomes negative 3 4x minus 7 over 2x squared minus 7x plus 5 squared. Okay. So there's our first derivative. Just doing a simple little, you could have done, again, quotient rule, chain rule, however you prefer it. But all we gotta do is plug 3 into that. So f prime of 3 equals, it's going to be negative 3 times, I think that's 5 on top, and on bottom it becomes 3 squared is 9, 18 minus negative 3, so that'll be 2 squared, I think, on bottom. You can check my math on that. That's negative 15 over 4, and that is the correct answer. Okay, so nothing too terrible about doing that one. Let's move on to B. B says find the x coordinate of each critical point. Okay, so we're going to find the x value of each critical point of f on the interval just between 1 and 2.5, and classify each critical point as the location of relative min, relative max, or neither, and justify your answer. All right, let's start with the justification of what a critical point is. So a critical point, by definition, is just a point where the derivative equals 0 or undefined. So critical point is where f prime of x equals 0 or does not exist. Okay, just what a critical point is. So let's start by finding those values. Okay, so remember that f prime of x from a previous problem was equal to negative 3 4x minus 7 over 2x squared minus 7x plus 5 squared. Okay. And to find our critical points, we're going to set both the top equal to 0 and the bottom equal to 0. Think about those points. On the top, what makes that 0, and you can do the math there, it's just going to be x equals 7/4, which is in our interval. Okay, that is in our interval from 1 to 2.5. That's like a little less than 2. And on the bottom, what makes this 0 is if you factor this, it becomes 2x minus 5 and x minus 1. And what makes the bottom 0 is x equals 5/2 or 2.5 and x equals 1, which you see are the endpoints of my interval that are not concluded, so we don't include those points. So the only critical point on this number line is 7/4. Okay, so there's your justification of finding our critical point. Now, identifying if that critical point is a minimum, maximum, or neither, we're simply going to think about the sign change at that point. So here we're at 1, this is 2.5, and we're testing right here at 7/4. And we're testing f prime of x, right? So like, so 7/4, maybe if I try 2, that's a little bit to the right of it. And remember, I'm testing that in my derivative. So if I plug, any number I plug in the bottom because it's squared is going to be positive. So I'm really just worried about the top here. If I plug in like 2 into that, that's going to be a negative times a positive, which is a negative on top and a positive on bottom. So we have a negative right here. And 7/4, so if I plug in some number a little bit bigger than 1 and a little bit less than 2, that's going to make this value here negative, and negative times a negative is a positive on top, so we have positive. So that means that 7/4 is a minimum. So x equals 7/4 is a minimum because f prime goes from positive to negative. All right, there you have it. That is that's B, finding your critical points and justifying if it's a max, min, or neither. All right, C. I'm glad that this problem finally popped up. Improper integrals here, okay, which is still part of our curriculum. Could be tested on, so it's a good thing it's popping up. It says using the identity that, so f of x is what we're given here, breaks down to this, and all that is just partial fractions, is fraction decomposition, right? Which we know how to do, and they just saved us the time and did it for us, okay? But it wants us to use that form to evaluate the integral 5 to infinity of that function and show that integral has a value or that it diverges. So let's remember how that works. Remember that if I'm going to do 5 to infinity of f of x, okay, how we deal with an infinite bound is we're going to change it to a limit, and we always made infinity r. So we're going to say this is the same thing as the limit as r is approaching infinity of 5 to r of f of x. Okay, so that's going to be 2 over 2x minus 5 minus 1 over x minus 1 dx. Okay, so we're going to integrate it with r and 5, and then we'll take the limit at the very end. Okay, so let's go ahead and integrate it. So this becomes the limit r approaches infinity, and integrating each of these quantities here, I'll do it in brackets here. The integration of 2 over 2x minus 5. You could do u sub and let it be 2x minus 5, and du is 2, but that actually just comes out to being the ln absolute value of 2x minus 5. Okay, that's the integral of 2 over 2x minus 5. And then minus the integration of 1 over x minus 1 is ln absolute value of x minus 1. Okay. And we are evaluating all that from 5 to r. Okay. All right. One thing the answer key did do that I liked, just to help us simplify the problem, is they went ahead and like combined this to one quantity because of our quotient rule for natural logs. We could say that this is the limit r approaches infinity of ln absolute value of 2x minus 5 over x minus 1. I just thought that was nice. Okay. I'm going to try to finish up here at the top right. If I plug r and 5 into that, so I got the limit r approaches infinity of, plugging in r, I got the ln of absolute value of 2r minus 5 over r minus 1 minus the ln absolute value of 2 times 5 minus 5 over 5 minus 1. Okay. Now, where the limit really comes into play is the quantity that has r in it, right? So if I take the limit as r approaches infinity, if you look inside ln, that's just a rational expression. A rational expression with equal powers on top and bottom, so we're just going to take the leading coefficients. So the limit of that rational is 2 over 1 which is 2. So this becomes, so the limit of this quantity here is just the ln absolute value of 2, which absolute value of 2 is just 2, so you don't need the absolute value anymore. And then minus this quantity becomes, what's that, 5 over 4, so 5/4. And there you go. Because we actually got down to a quantity, this actually does converge. This integral does converge to a value that it does not diverge. And that's my answer. The answer key actually simplified it by, again, combining it to one natural log using division. So they did the, and I'm going to stop doing absolute value. They did 2 divided by 5/4, which is actually 8/5. That's my answer. Okay. So that was cool. Improper integrals. Been a while since we've done that, so hopefully that made some sense and kind of rings some bells. Okay. And then this last one here. This last one, I guess, is not required for you to know. It's using something that's not in our curriculum anymore, but I still think it's something we did learn optionally, so hopefully we kind of remember it. It says determine whether the series now. Okay, so we're using the function and now we're creating it as a series. We're saying, I'm asking, does this series converge or diverge? And state the conditions of the test used for determining the conditions, determining convergence or divergence. Well, here's kind of what they wanted you to do, is they wanted you to recognize, okay, well, what we just did with this in part C is we took the integral to infinity, which that is actually a test for convergence and divergence. This is actually using the integral test. And I'm gonna write down, kind of refresh you on what the integral test says. So the integral test states that if, all right, I'm gonna write it out the nicest way I can. So if we have this right here, if we have the summation n equals, in this case, 5 to infinity of f of x. Okay, so if we're trying to figure out if that series converges or diverges, if the integral of 5 to infinity of f of x, so if the integral of the function converges, then the series converges. Okay, and that's really about it. The fact that okay, so the criteria in order to do the integral test is that number one, the function is always positive, and it is positive from 5 to infinity. Number two is that it's decreasing. And if you use your derivative from part A, you could tell that f prime of x is always going to be less than 0 for the domain 5 to infinity. All right. And then lastly is that it's continuous. And this function is continuous except at the points 1 and 2.5, but it is continuous on the interval 5 to infinity. So that's the integral test. As long as those three things are true on the interval 5 to infinity, that it's positive, which it is, decreasing, which it is by the derivative, and continuous because we're past the points of asymptotes there, then the integral test applies. And since the integral test converges, then so does the series. And that's kind of the connection it was wanting you to make. Okay, so let's kind of look at the answer key there. Part A, we got 2 points for finding f prime of 3. We got negative 15 over 4. Part B, we found the x coordinate to be 7/4, the only one on my interval. We said it was a maximum with justification. Part C, we got the correct antiderivative. So here, the limit expression, so we got the correct limit expression. All right, and then the answer, which was the ln of 8/5. And then lastly, 2 points, it was the answer with the condition. So you see that it says, hey, f is continuous, positive, and decreasing on the interval. So the series converges by the integral test, since from part C we found that this converges. Now the other way that they did it was the limit comparison test, which again is no longer on our curriculum, so you can read through that if you want. All that says is if we can create some function b sub n, which in this case they said was 1 over n squared, which we know converges by p series. They said, all right, well, if I can take the if I can do a limit comparison, meaning I'm gonna take the limit of a sub n divided by b sub n, and that limit actually ended up giving us a value, and if we have a value, if that actually converges, and our b sub n converges, then the function that we started with also converges. So that was a test we did a while ago. Again, it was kind of optional, so D was more so, I guess, optional at this point, but it was a good test, I guess. But the biggest one I would use in that one was integral test, since we did the integral in part C. Okay. All right, let's move on to 6. So 6 was, again, a little bit of a doozy. Part A, you should hopefully be able to do. In part C, B and D, I guess, are more so not the ones you need to know, but let's try A, at least creating a Maclaurin series. Okay. So it looks like at the beginning of the problem here, it says f of 0 is equal to 0, f prime of 0 is 1, and any derivative after that, f of n plus 1 of 0, is equal to negative n times f of n times 0. Or not times 0, of 0, that's the center, for anything greater than 1. This looks confusing, but all this is stating is to get our next derivative, take the previous derivative and times it by negative n, which we'll do in a second. Okay. It says the function has derivatives of all order between negative 1 and 1, and the derivatives of f satisfy the conditions above. The Maclaurin series converges for anything absolute value of x less than 1. Okay, that's good. So it says, show that the first 4 non-zero terms of the Maclaurin series of f is this, and then write the general term. So we kind of already got our answer for A. It told us what it's going to simplify down to. We just got to show that. So let's start from our roots here. Okay, let's start with the general formula for the Maclaurin series. And I'll write that up here at the corner. For Maclaurin series, remember the definition says it's going to be f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0x cubed over 3 factorial dot 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 f n 0 x to the n over n factorial. So that's your basic Maclaurin series formula. Okay. So now, in order to create this for this particular series, we need to know f of 0, we need to know f prime of 0, f double prime of 0, f triple prime of 0. We need to know the first 4 terms. And it's the first 4 non-zero terms. So if you notice, the first term is 0, which means we're actually going to need to go to our next term, f to the 4th derivative of 0. Okay, so we need to know all 4 of those in order to do this problem. Okay, so we got the first 2, and I'll just kind of I'll write it over here to the side. So we got f of 0 is 0, f prime of 0 is 1. We need to know f double prime of 0. Okay, f double prime of 0. Which, what this is saying is to do negative n times f n 0. So this means so this is my 0th term, this is my 1st term, this is my 2nd term, so forth, right? This is saying to take the previous n value. So the previous n value in this case, if I'm doing f of n plus 1, that's f of 2. The previous n value is f of 1. So actually, I'll just write it out this way. I think this is the best way for you to see it. If I want to know the second derivative, that's going to be f of 1 plus 1 is 2. So n is 1 in this case, of 0. is equal to, it's going to be negative 1, all right, and then times f first derivative of 0, which we see is 1. Okay, so this is equal to negative 1. Okay. For f triple prime of 0, it's going to be the previous n, so in this case it's going to be negative 2, and then times the derivative of f double prime, which was negative 1. So this is equal to 2. And then f fourth derivative of 0 is going to be negative 3, so the previous n value, and then times the derivative of the previous one, which is 2, which is equal to negative 6. Okay, so there you have it. We have all of the terms that we need. We can write it out. Okay, so I got that if I write all these terms, I got 0 plus f prime of 0 is 1 times x plus f double prime of 0 is negative 1 times x squared over 2 factorial. Plus f triple prime of 0 is equal to 2 x cubed over 3 factorial. And then plus f fourth derivative of 0 is equal to negative 6. That's x to the fourth over 4 factorial. So we got our first 4 non-zero terms, and if you simplify them, it is going to simplify down to this. This is going to become x, and then minus x squared over 2, and then plus 2 over 3 factorial just becomes 1/3, so that's going to be x cubed over 3, minus 6 over 4 factorial, that's 6 over 24, or 1/4, so x to the fourth over 4. And you can kind of see what the pattern is going to be. Plus dot dot dot. The general term is, well, first of all, it's alternating, so that's going to be negative 1 to the n plus 1. Because now that we got rid of that first term here, or the 0th term, we got our first, second, third, and fourth terms here. So that's going to be negative 1 to the n plus 1. And it looks like it's just going to be x to the n over n. So there you have it. It's the first 4 terms and the general term after plugging in our derivatives into the Maclaurin series formula. Okay, so I mean, if they're asking you to create a Maclaurin series, that's what they're going to do. They're going to give you some formula to figure out the derivatives. You got to plug it into the general formula and simplify it down and come up with a general term there. Okay. All right, let's move on to B. B is talking about absolute and conditional convergence, which again was part of an optional lesson. It was actually a part of a mandatory lesson, but it was an optional piece of it. So I don't know. We'll see if you remember it. But it says determine whether the Maclaurin series in part A, so you can remember the answer we just got, converges absolutely or conditionally or diverges at x equals 1. Okay. So at x equals 1, if I plug 1 in for x into the summation or the series that I came up with in part A, I am going to have the summation n equals, we started off with the first term in this case, to infinity. It was negative 1 to the n plus 1, and now it's going to be 1 to the n instead of x to the n, and 1 to the n is just 1, so that goes away, over n. Okay, so let's just kind of refresh ourselves on the difference between absolute convergence and conditional convergence. Okay, how that works is talking about, like, if you think of absolute, I'm thinking of absolute value. So it's saying that if I have, what's the best way to say this? All right, if the series n equals 1 to infinity, and I'll just call this a sub n. Okay, if the absolute value of this converges and just the regular old one converges, so n equals 1, okay, then it absolutely converges. Okay, if both of those are true, then it absolutely converges. Now, if just this one is true, but this one is not true, then it just conditionally converges. All right, it just conditionally converges. So if the part that's not the absolute value converges, then it's only conditionally. Okay, so if you think about this, this right here is an alternating series. So you can actually discuss this convergence based off of an alternating series test, which is something you need to know. Remember, the alternating series test had two requirements to determine if it converges. A sub n, which in this case is 1 over n, it's the piece without the alternating series part. If I take the limit of that, does it equal 0? Yes, there's a check there. And is it ultimately decreasing? So if I said that f of x is equal to 1 over x, then f prime of x equals negative 1 over x squared, which is always less than 0. So it is always decreasing. Okay. So that's our two criteria for the alternating series test. So you can say by the alternating series test, I'm just going to draw an arrow for, well, I'll say that the summation n equals 1 to infinity of negative 1 n plus 1 over n converges. So right now, I know that this converges. I know that piece of it does. But what I'm curious about is if the absolute value of that converges, which that's going to be the summation n equals 1 to infinity. The absolute value is going to make that negative on top go away, so it's just going to be 1 over n. And we know that this is the harmonic series, and we know the harmonic series diverges by harmonic series. So if that's the case, then that means it only converges when I don't take the absolute value. So that means that the answer to this is going to be conditional convergence. It is conditionally convergent because the absolute value part does not converge. Okay, it's a very classic example of that's actually the example we used when we talked about conditional convergence. So pretty good problem. All right, I'm kind of running over here. Sorry. Let's move on to C. C says write the first four non-zero terms and the general term of the Maclaurin series for g of x, which is just the integral of f of x. So that's actually super easy as long as we got A. So g of x is equal to the integral 0 to x of f of t dt. So that's just this. That's just what we got in part A. So I'm going to say that's t minus t squared over 2 plus t cubed over 3 minus t to the 5th over 4 plus dot 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 all the way to the general term, which was n to the oh gosh, sorry, not n, x or t, I guess in this case, t to the n over n. So let's integrate it, and that's our answer. So integrating this, and then plugging x in, and then plugging 0 in. But if I plug 0 in, it's all going to go away. So really, it's just we're worried about plugging x in. If I integrate it, it's going to be, let's see, t squared over 2 minus, let's see, plus 1 will be t cubed over 6 plus t to the 4th over 12 minus t to the, is that, wait, why did I write 5 there? I meant to write 4 there. So 1, 2, 3, t to the 5th over 20 plus dot dot dot, and then that integral is going to be t to the, oh, and I forgot the alternating series piece in this part, I'm sorry. So that's negative 1 n plus 1. So the integral, that's going to be negative 1 to the n plus 1 t to the n plus 1 power now, and when I divide by n plus 1, I got n plus 1 on bottom, and then times n, okay? And we're going to plug 0 and x into that, and really plugging 0 into that's going to cancel everything out, so it's just going to plug x. So let's write the final answer at the top here. G of x is equal to x squared over 2 minus x cubed over 6 plus x to the 4th over 12 minus x to the 5th over 20 plus plus negative 1 to the n plus 1 x to the n plus 1 all over x plus 1 times n plus 1, sorry. N plus 1 times n. Okay? And that's our final answer. That's the integral of what we just came up with in A. That's all part C was saying is take your answer from A and just integrate it. And that's what we did. Okay? I'm over 30 minutes. Sorry. And then lastly, part D. Part D is an integral test, an error bound, which they completely cut error bounds out for y'all, so that's good. But this is the error bound for an alternating series, so that's one that's a little bit more relevant. So maybe you tried it. But it says let p sub n of 1/2 represent the nth degree Taylor polynomial for g about x equals 0 evaluated at x equals 1/2, okay, which is a part of our interval of convergence, where g is the function defined in part C. So what we wrote down is our final answer in C. Use the alternating series error bound to show that this right here is the difference in, and I don't know why they switched the order here. This is the estimated value of g of 1/2 using the first 4 terms of the Taylor polynomial, and this is the actual value of g of 1/2. It wants us to estimate that error and show that it's actually less than 1 over 500. How we're used to seeing this formula is S, which is the actual infinite sum, the actual value of g of 1/2, minus the partial sum, which in this case is p sub 4 of 1/2. And we want to show that that's less than, and how the alternating series test works is that the error is going to be less than the next term in the sequence, which we said was a sub n plus 1. Okay? So if I'm using the first 4 terms, it says right here, first 4 terms to estimate it, it means that my error is going to be less than the 5th term. Okay, so how we would write this, I'm going to say the absolute value of g of 1/2 minus p4 of 1/2 is actually less than my next term. And that next term is that x to the 5th one, right? So it was actually x to the 5th, which in this case x is 1/2. So that's going to be 1/2 to the 5th over 20 was what it was from the last problem. And notice I didn't put the negative. It was minus. I didn't put the negative because it's just the term, the absolute value, not the actual negative piece. Okay, which this is actually equal to. That's actually going to be 1 over 32 times 20, which is 1 over 640. And that is less than 1 over 500. So there you have it. We showed it. So I wouldn't stress too much about that one, but it's not a bad. I like that error bound more than any of them because all you have to do is just show that the difference is just less than the next term. So as long as you know the next term, you know what the error is going to be. Okay. All right. Here's my answer key here. We get a point for finding all of the correct derivatives from our part A, for verifying the terms. So that's plugging it into my Maclaurin series formula and simplifying it down, and then 1 point for getting the general term. B was that it converges conditionally with reason. They discussed it as it says does not converge absolutely. So converges conditionally. They talked about it in terms of harmonic series and alternating harmonic series, but I think the way we did it was just fine. C was that we found the first two terms and the remaining terms and the general term of just the integration, which we did. And then D was just 1 point. So it wasn't the most stressful thing in the world, but it was 1 point doing the error bound. But yeah. All right. Well, that was the rest of 2017. Hopefully you got at least part A and C, or at least part A and C made sense on this problem once you were done. Those are the ones that I think are the most important. And please let me know if you have any questions.